Hello, we are doing lesson 6.3, vectors in the plane. And it starts off saying many quantities like temperature or time can be represented as a single real number. Quantities that have both magnitude and direction, like force and velocity, cannot just be a single real number. So this is kind of physicsy. And then, sorry if you can hear all these text messages. The blanks are giving you how to write a vector PQ. It has like half an arrow on top of it. And then how to write magnitude. It almost looks like absolute value, but two lines instead of just one on either side. And then magnitude is the same thing as length, which we find with the distance formula. I'm behind my writing. And then the same magnitude and same direction mean that two vectors are equivalent. So we are going to look at the vectors u and v in number 1 that are given by those points. So I'm rewriting the points for point P and Q. And I want to show that they're equivalent. And so I'm going to see if they have the same magnitude, so the same distance between the two points. All right, so just plugging in for the distance formula. We find that vector PQ has a length or a magnitude of root 13. And then this is for vector RS. Doing the distance formula again with those 2 points. All right, and you can already tell here when we get to 3 squared plus 2 squared that we are going to end up with the same length for both of them. So that's good. And then we have to show that they have the same direction. This is a little less direct, I guess. Same direction is going to mean same slope. So the slope formula, if you've forgotten, is y2 minus y1 over x2 minus x1. Remember, rise over run. So it ends up being what's in parentheses. So do the y's over the x's, and you end up with a slope of 2/3 for PQ, and then also a slope of 2/3 for RS. So these two are equivalent, which was what we were asked to show. All right, on this page, we are talking about vectors whose initial point is the origin. That would be in standard position. This can be represented by a vector instead of points has these pointy brackets, I guess, that look more like vectors. They look like arrowheads instead of the curved parentheses. And then a zero vector means that it starts and ends with the origin, which makes sense, you know, 0 doesn't go anywhere. And then the component form is given by PQ equals, this bold formula, Q1 minus P1, comma, Q2 minus P2. So it kind of seems like the distance formula. And then the magnitude is given by the distance formula again, and then that will end up giving us V1 squared plus V2 squared. If you look back in the first spot, when you subtract the x's and the y's, it's called V1 and V2 in those funky pointy brackets. So then if you've already found that, you can find the magnitude more easily. So in number 2, we're trying to find the component form, so the V1, V2. So that's the first bold underlined formula. And we're trying to find the magnitude of the vector V. So I'm going to start off by doing V1, which is Q1 minus P1. And then V2 is Q2 minus P2. So I'm basically just subtracting the x's and subtracting the y's in the same order. This gives me the component form of -5, 12. So this means if I move this vector to the origin, its terminal point, its end point where that arrow is going to be at -5, 12. All right, and then we need to find the magnitude, so that's going to be V1, which is now -5 squared plus V2, 12 squared. So this is giving us the length of the vector. I don't even think I said what a vector is. I said it's a line with, you know, direction and stuff, but it's basically a line segment, or I guess it's more like a ray but it doesn't keep going forever. It has an endpoint, but it looks like a ray on a graph. I am so sorry, I never even said that. All right, I'm about to draw what a vector is. So when we are adding, you just add the x's together and add the y's together. So that's a vector u and a vector v. If you're adding them together on a graph, it actually looks like v being added on, being tacked on to the end of vector u. And then the vector u plus v is actually from the beginning of u to the end of v. So that's what the new vector would look like. Scalar multiplication, this is when we just multiply it by like 2 or 4 or -2 or whatever. And it doesn't change the direction or anything. It just is going to make it longer or shorter if it was a fraction that we multiplied it by. All right, but we are just going to be doing these operations. It's not much different than typical operations. 2 times vector v is 2 times -2 and 2 times 5. So you distribute the 2 to both coordinates of the vector. Right, and then so that I could see the points. This one is w minus v. So the same thing when you're subtracting, you need to subtract 3 minus a -2, so add 2, and then 4 minus 5. So distribute the minus to both of them. So I'm subtracting the x's of v from the x's of w, and the y's of v from the y's of w. All right, this last one, -2, 5, that's v, plus 2 times w, and just like in regular operations, you're going to do multiplication first and then add them. So just multiply the 2 to the w, and then when you add them, you end up with 4, and 5 plus 8 is 13. Right now we only have 2 more problems with new vectors. And we're done. All right, u plus v again. So add the x's together, add the y's together. 4 plus a -4. Obviously, it took me a while to figure out. It was 1. And then 3 plus 0 is 3. And then 2 times u minus 3 times v. So I distributed the 2 to both of the u coordinates. So that's 10 and 6. And then I distributed a -3 just because I thought that would be a little easier to add them in the end. All right, so 22, 6. That's all.